Okay, so for our first keynote, we would like to welcome Hannes Siebenhandl. Hannes made his very first open source contribution in 2018 to the Haskell Language Server, and since then he has become the maintainer for quite a lot of libraries and tools in the Haskell IDE ecosystem. And maybe for those long-time Haskellers who started before Haskell Language Server was around, you may know the pain it was to set up a somewhat functioning IDE using Vim or using Emacs back in the days, and now it is so much simpler. You have you just install a VS Code plugin and that's it. And Hannes is, well, to a large degree, we have to thank Hannes for that, because of the tools that he wrote, that he's a maintainer on, that he contributes to. And yeah, so today he's going to be talking about exploring the Haskell Language Server. Thank you, Hannes.
Thank you for this great introduction. And hello, everyone. Today, I want to take you through the Haskell language. I want to explore with you the Haskell Language Server. I want to explain to you the greater architecture of what makes the modern Haskell IDE experience. And I want to make a deep dive into some of the internals of the Haskell Language Server. And to do that, I want to take a look with you at the cabal-plugin. So, without further ado, what is the cabal-plugin? In advance, some parts of these slides will not be readable from the back of the room, so I'm sorry for that. But yeah, if you want to read it, then you have to come closer. So, what is the cabal plugin? Well, the cabal plugin, also called HLS cabal plugin, is an extension to the Haskell Language Server and provides basic IDE features for cabal files. So, for example, it allows you to get diagnostics like errors and warnings when you forgot something, when you forgot a required key. It offers you completions for certain key value pairs, and you can also format cabal files with one of the two main formatters that we currently have, cabal-fmt and cabal-guild. And it also has some advanced IDE features, like you can go to definition for certain constructs in a cabal file. So, for example, you can jump to the definition of a so-called common sections. You also have what you will later see. You have a file outline so that you can see at a glance what is actually in your cabal file. And I want to thank various contributors, because this plugin has been primarily contributed by Google Sum of Code students and Haskell Language Server and Haskell Sum of Code students. And well, without them, this wouldn't have been possible. So great thanks to them. So since this is not really telling what the cabal plugin actually do, we're going to do a very small, very short demo where we're also going to talk about where we are also going to tease what we are going to look into in more detail later on. So I'm going to switch to the code editor. What you can see here, I hope everyone can read it. Actually, can everybody read it? Or like roughly at least, can see what's happening. So on the right side of what you see here is a very simple cabal file. So this cabal file has been generated with the very nice tool cabal init. So this is what you get quite easily, and it's very nice and very helpful for getting started on a Haskell project. And on the left side, you have some very extremely important Haskell source file where we greet the hackathon. Hello, MuniHac. And the features I want to show you now is just illustrate what the basic IDE features are with the cabal plugin. So one of the most important features is if you, for example, let's do this one. If you, for example, misspell a keyword, you immediately get a warning that this is an unknown option, which is very helpful for all the people that tend to keep forgetting the names of certain options. You also get completions for many of these key value pairs. So, for example, when you don't remember the GHC options that you always need, you can get some completions, and we also have completions for some enum fields. For example, maybe some of you know the build type of a cabal file. We're not going to go into that, but it is in essence it's an enum with 4 different values. So, for example, we get all 4 of these offered. We still want it to be a simple cabal file, so we're not changing that, just to illustrate what we can do. And other cool things is, for example, we get also completions for the exposed modules. So if we deleted this module, we get completions that we might want to add this module to our cabal file without having like to look up where it actually is, and that's, at least for me, it's quite helpful. We also get the same completions for the source directories. So I'm assuming we didn't have any source directories, we would get some suggestions. So for example, what things you might want to include into your Haskell project. And one thing why I'm also very much interested into this cabal plugin is that cabal files, as you are able to see, do not live in isolation. What does that mean? There is some interconnection between the Haskell files and the cabal file that you have. So for example, as I've just shown you, you always need to add a module to a cabal file when you add a new one. The same goes for when you add a dependency. For example, if I wrote here, if I try to add, like if I import a module from a dependency I'm not depending on right now, like let's take, for example, this data list split, then this will have a red squiggly line, which we call diagnostics. And this error, which is generated by GHC, will tell us actually exactly what we need to do. So it tells us we do not depend on the split dependency. We may have to add it to our cabal file. And that is kind of like a common pain point in the Haskell development. Whenever you add something new, you also have to go to the cabal file and update it. And there's a very little nifty tool already around called cabal-add, which takes care of this issue. It's a CLI tool. And you can invoke it and say, please add this certain dependency to a certain component. So a component is this library, for example. That's what we call a component. And, oh, big cursor. Sorry, I was surprised. And we can, and in fact, in the Haskell Language Server, we can use this cabal-add tool to provide a so-called code action fix, which is this little lovely light bulb. I hope everyone can see it here. And when we click this, we can actually, HLS, or more in particular, the cabal plugin, can offer us to add the dependency that we are still missing to our cabal file. And if we click that, amazingly, we now have a new dependency. Unfortunately, due to a small bug, we still have to manually reload the Haskell Language Server, but that will be fixed in the future. At some point, this will work flawlessly, at some point. So, and now, I think I can prove, well, it doesn't look red. Yeah, well, looks fine to me. So, that was the small demonstration of the cabal plugin. And this particular code action that I've just shown you is what I want to explore in more detail, and we want to look behind the curtain of what is happening inside of the Haskell Language Server when we have these when we try to execute these code actions. Okay, luckily this demonstration worked out flawlessly, almost. So I'm very happy about that. And first things first, we have to take a look at the full picture of what actually encompasses the IDE experience in Haskell. When I'm talking about the IDE, when I'm talking about the IDE experience, there are actually three major parts involved. The first thing that we have is the language server, which is like the Haskell language server. Usually there's a language server for each individual programming language, and the HLS is the Haskell language server for the Haskell programming language. So, but this is the backend. So it does not actually take care of what you see in the edit. It does not actually take care of what you see in the editor. And that's the second component. We always have like some kind of editor component, which is the client of this architecture. And that can be anything. That can be anything essentially, any kind of code editor, such as Sublime Text, Vim, VS Code, or Helix, or anything that you can think of. And these two components need to communicate in some way. And the way they communicate is via the so-called language server protocol. The language server protocol is kind of describes how these two communicate, how the client and the backend, or like in this case, Haskell language server, shall communicate, and how the IDE features are implemented. We're going to take a brief look at what the language server protocol roughly looks like. So the language server protocol, essentially it is just specifies what kind of messages are supposed to be sent between a front end, like the LSP client, such as VS Code, Helix, Emacs, and so on, and with the IDE backend, HLS. It specifies JSON messages, to be precise, JSON RPC messages that are sent between those two components. And notably, there are two major patterns for communication between those components, and it's like the request-response pattern. So when, for example, the client, like VS Code, sends a request to HLS, then HLS has to respond with something, or like according to what the request looks like. And then there's also the notification pattern. A notification is in the notification pattern, the client only sends a notification informing HLS that a certain event has occurred, but it does not require the language server to actively answer to that request. And that does not mean that the language server is not allowed to do anything with it. So it might actually do a lot of it, it might actually start a lot of work, but it does not need to respond to this. It does not need to respond to this LSP message. So it is asynchronous. For the rest of this talk, we're seeing here we have while we have one language server, we may have many different code editors. Again, such as VS Code, Emacs, and so on. And for the rest of this talk, I'm going to uniformly refer to any code editor as VS Code. There's no reason for that other than it's much more concrete than saying LSP client, which would be a much more generic term. But since there's a lot of abbreviations already, so I'm trying to be more concrete. And so whenever I'm referring to some code editor, I'm referring to VS Code. But nothing we're going to look at is actually in any kind specific to VS Code. So it works the same in any other code editor, such as Vim and so on. So now that this general architecture is out of the way, let's go back to the code action that we've just been looking at. So the first thing that happens. So we have here to the right, we have a control flow diagram where we have isolated the VS Code component and the language server component. And they communicate with each other via the language server protocol. And the first thing that happens is when you as a user type anything in your editor. So like, for example, what we wrote is we want to import the data list.split module. VS Code then sends a change notification, so HLS will not respond to that message. But when HLS receives this notification, it will update its internal state and to reflect the latest changes from the code editor. And then it will start the heavy machinery. It will say, okay, now that this Haskell file has been updated, I want to parse it, I want to rename it, I want to type check it, and then I want to provide useful diagnostics to the user. And when it's done with these things, it will send back diagnostics. Diagnostics are a more general term for errors and warnings and code lints, for example. So I will use the term diagnostics, but you can think of them as being essentially everything's a diagnostic that has these lovely squiggly lines here, or like that you can see here. That's what we call a diagnostic. And when we enter this line import data.list.split, then GHC will tell us, well, you do this. I cannot resolve this import. You do not depend on the package split, which then the code editor will display to the user. What the user then has to do, the user will click on that error, and when that happens, when the user clicks on this diagnostic, then VS Code will send a request to the language server and ask the language server, do you have any idea of how to fix this error in particular? And then the language server, this is different to the notification. This is a request response pattern. So when the VS Code asks HLS, do you have anything to fix that? HLS will then respond to that request, and perhaps it will offer some fix. So in this very particular instance, it can figure out, I don't know what this input is, but I do know a package that exposes this module. And then the user gets like a list of potential code fixes. In this case, this list is very small. It's exactly one element. Good enough, I would say. And then the user can choose to accept this quick fix, or like this code action fix. And what that happens then is then the VS Code will apply the change that was suggested by our Haskell language server and apply it to the local file. And when that happens, afterwards, naturally, the VS Code will then send a change notification to the Haskell language server, telling it that the cabal file has changed. And any questions about that? About the general flow of a code action? Great. So
then the code action is just a description and a like textual if.
sorry, what is it?
The code action is just like a description and a textual if.
Yes. Yes. So the question is what is contained in a code action. A code action is basically, or like you could boil it down to like a title and a text div where it's like where it contains only the change that you actually want to make. Yes. Okay. So now that the general LSP workflow is clear to everyone, we want to focus on what is happening exactly in HLS when code actions are requested and when we produce them. And so, to understand that, we have to take a look at the general architecture of the Haskell language server. Haskell language server is not a single binary. In fact, it is it's a collection of compile time plugins, and it is a compile time plugin because we can only change what plugins are available at installation time. So we cannot add new plugins or remove plugins during runtime, but we can add them during installation time. And HLS is actually fully implemented using these plugins. There's very little that's actually built into the Haskell language server itself. And to the right, in this graphic, what you can see here is you can see what HLS kind of looks like when you would be looking at it from a distance. Let's say from a distance. I have here a selection of the plugins that are featured in HLS. So, for example, we have a completions plugin, which only takes care of responding to completion requests. So when VS Code asks, what could I show to the user, what identifier they could mean. And that shows that plugins can be incredibly specific to a certain purpose. So plugins can be incredibly small, just like only offering completions, or they could be incredibly big, such as the GHCID core plugin, which drives the main pipeline of the Haskell language server. This makes sure that your Haskell files are actually parsed, type-checked, renamed, and so on, and provides the most important diagnostics that you see whenever you launch HLS. We also have, as hinted, the HLS cabal-plugin, which takes care of providing diagnostics for the cabal file, like the basic IDE features. And then we have dozens, like literally dozens of other plugins, such as the HLS refactor plugin, which takes care of certain refactorings. And plugins are also very nice for isolating certain components, and they can individually decide or like specify whether they can handle certain LSP requests. And what does it look like? So when VS Code sends us asks the language server whether there are any code actions available to fix this particular issue, what happens then? So VS Code sends a message, and it asks us what code actions are available at a certain location in a certain file. And HLS then takes this message and distributes it to all the plugins and asks the plugins whether they could handle such a request, whether they are capable of handling these code action requests. For example, the completions plugin will respond, no, I do not know how to handle such requests. GHCIDE core, as it only handles the core implementations of Haskell type checking, also does not know how to handle code action requests. However, our cabal plugin that we introduced specifies that it can handle these code action requests in practice. Similarly, HLS refactor plugin does also know how to handle such code action requests, and could, in theory, also respond to this particular request from the client. Okay, so now that we know that HLS consists of basically only of plugins, what is the interface of these plugins? A plugin is basically basically just a record. Nothing too crazy about it. So to the right, what you see here is a selection of the fields that describe what a plugin looks like. So first, we're starting out with the metadata. So plugins have metadata. So for example, a plugin has a unique identifier, which is helpful for log messages and error messages, so that we can tell if something goes wrong, in which plugin did it go wrong. Plugins also have a description. So that is, for example, for the user, where the user can say, where the plugin can then tell the user what kind of features it actually provides. So that's also like a user-facing feature. Plugins also have a priority, because some plugins are more important than other plugins. So for example, the type checking is more important than, well, all kinds of refactor plugins, because the refactor plugins cannot work if no type checking is available, right? Makes sense. And then we have one of the reasons why plugins are so extremely extensible in Haskell Language Server. We have the plugin file type. What we specify in the plugin file type is what kind of source files is this plugin able to handle. So a Haskell plugin, for example, can handle, would specify that it can handle requests for files that end in .hs or .lhs and so on and so on. A cabal plugin specifies here that it can handle requests for .cabal files. And at last, we have a configuration entry. What is in there? Well, in this plugin config descriptor, we basically have some information. What is this plugin enabled currently? Are specific things enabled? Does this plugin have extra configuration? So for example, whether you can configure how many completions should be displayed to the user, and similar things that the plugin can then honor. So the core of a plugin now are these fields. We have these three record fields. So the first thing we have are these two, and these are the kinds of these are the handlers that allow the plugin to declare what kind of LSP message this plugin is able to handle. So the first thing, the plugin handlers, is capable of handling any kind of LSP message that follows the request response pattern. So in other words, when there's a request, there will be definitely a response. And in the second, the plugin notification handlers, we can say that a plugin subscribes to certain LSP notification events. So for example, when a Haskell source file changes, we can subscribe to these change events, and if they change, we can start type checking these files. So that's essentially what happens in the core plugins. And at last, we have the plugin rules. We're going to look into the plugin rules in more detail later on. So let me just say very briefly, rules are used for caching expensive computations when you are writing the implementation of a plugin, like when you write a specific plugin handler. They are also useful to store plugin-specific state across multiple requests, so that if you need something over multiple generations. And you can also access the global state of all of HLS, essentially. Okay, so how do we now write a plugin that is actually capable of handling code action requests? And it is, at least I would claim so, surprisingly simple. What we need to do, I hear laughter. Someone's not believing me. Okay, so what we basically have to do, we have nice little utility functions, such as this default plugin descriptor, which basically generates a basic form of this plugin descriptor that we've just seen, fill in all the gaps, and that's basically it. It basically generates the empty plugin descriptor. We have to pass in a plugin ID, which is provided from the outside world. The outside world makes sure that the plugin ID is indeed a unique identifier, so you do not have to come up with a hopefully unique ID on the spot, but it will be, you can assume you will get a unique ID. What I've highlighted here is a description. So this little thing is the description of what the plugin can do. And then you simply override exactly what you need. So for example, in this example, what we do is we provide one specific handler for the request response pattern to respond to requests for code action requests. Just a word, this S method text document code action, which looks very scary, is basically just our internal name for code action requests. there's like a lot of machinery that makes sure that everything is type checking correctly, and this is part of it. It looks dangerous, but it's rather benign in comparison. And when we have this MK plugin handler, we say, okay, this handler can respond to code action requests. What does this cabal-add handler look like? We're going to find out, whether you want or not. So I promise this is the, no, I'm not promising anything, taking it back, that's the next slide. So the cabal-add handler is relatively speaking a straightforward function which takes 3 parameters. The first 3 parameters are these, like the first parameter is the IDE state. The IDE state is a collection of global variables that we might need access to later when we try to respond to a certain request. We're going to talk about this in more detail later, but for now, it's just a collection of global variables that we all have access to. Second, we get the plugin ID. The plugin ID is, again, mostly used for error messages or when you want to log something, and often we don't need it because, well, the rest of the infrastructure takes already care about tagging error messages with the correct plugin. And then the third parameter, which is also kind of, in this case, the most interesting parameter, is the code action parameters. The code action parameters are the parameters that are sent by VS Code to tell the language server for what particular position and in what particular file we are requesting the code actions in. So for each request, these parameters may look different. For code action requests, they contain 2 important pieces of information: the cursor position and from which file, or like in which file we are actually asking for code fixes. And now we're briefly looking at the cabal-add handler. How we are approaching implementing this code action. So first thing is we need to know what diagnostics are actually active at the cursor position that we just selected. That's what we do in this step, and then we get some collection of diagnostics. These are like exactly the diagnostics that you also see in the diagnostics that you also see in the code editor. If there are none in this code, if there are no such diagnostics in the cursor selection, that's in general no big issue. But for this particular implementation, it is, because what we do is based on the GHC error message, we actually, well, since GHC already tells us what package we want to depend on, what we do is we do not try to query on Google or something what may export this particular module. We just take the error message that we've just seen and use a regex, which is, you can see down here, to pass the error message and extract the package that we actually want to add to our cabal file. This may actually change in the future. Hopefully it will change in the future, that we do not need to use regexes and rely on a specific error message format. Since GHC recently, like 6 versions ago, I think, introduced structured error messages. So maybe we can use those in the future. Okay, so if none of the diagnostics that we found at the particular cursor position looks like this error message, then this handler will abort. Because we cannot continue, like we cannot offer any code action if the errors that the user sees are not actually about missing dependencies, right? So that wouldn't make sense. We don't want to suggest adding packages that you don't need. So in this case, the error path is omitted, but you in this case the error path is omitted, but you would need to handle that error at this location. And the next step is assuming that we found a dependency. Then we can actually go to work, because then we know, okay, we have a dependency that we could add to the cabal file. And now I'm promising this is the worst code that you will see today. So we're going to take some time to look at it. I hope everyone can read it. It's a little bit small, I'm afraid, but yeah, well, I hope my explanations will just explain it without you having to read the code. So what we actually have to do when we want to produce a code action, when we already know we have a dependency that we want to add to a cabal file. We have, again, the 3 parameters. We have the collection of global variables called the IDE state. We have the original parameters because we need them. And we have the dependency up here that we want to add to the cabal file. So now there are 4 steps involved to produce a code action that does exactly what we want. The first thing is we need to find the cabal file. So you remember we clicked in the Haskell source file, but that we want to fix a dependency issue. But to which cabal file does this Haskell source file actually belong to? What we do is basically we look at the Haskell source file, and then we look in every parent directory whether we can find a cabal file, and then we will assume hopefully that's the correct cabal file. So that's the first step that we need to do, and we get the original and we get the Haskell source file location from the code action parameters. So they are provided by VS Code. Then what we need to do is we need to prepare some information about that cabal file. For now we will skip a little bit over that. What we intuitively need to do is we need to find the package description of that cabal file. So we need to parse it, and we need to make sure that it is a well-formed cabal file, and that we can figure out what components are part of that cabal file and what module belongs to what component. Because we need that in the third step. In the third step, we want to add a dependency to a specific cabal component. Remember, there can be multiple components: executables, libraries, test suites, and we want to add the dependency to the correct cabal component. We don't want to add it to every cabal component, and we also don't want it to add it just to the library component. So what we do is we take this package description that we have just obtained, and then we ask it in some arcane manner, okay, do you know whether there is like a Haskell, whether this particular component exposes this Haskell source file? And then, when this is the case, again, if that's the case, then we can do the second step. We can call the nice tool cabal-add and invoke it with the component that we want to modify and the dependency that we want to add to that component. However, we also need something more. Cabal-add also wants access to the original sources, because it needs to pass the cabal file to a certain representation that it can modify, so that it doesn't need to reprint the full cabal file, but only modify exactly what is needed to add this particular dependency. To do that, we have to do another action in this step, to be precise, where we say, intuitively speaking again, what are the sources of that cabal file at this very moment? And then we call cabal-add, and cabal-add will produce a new cabal file where the new dependency has been added to the correct component. So old cabal text and new cabal text are really sources. They're not file paths, they are the sources, or like the contents of the cabal file. And once all of that has worked out perfectly, hopefully, then we can actually build a response. The response then has to be, as we have pointed out, we need a title. So for example, we produce a title for the code action that is displayed to the user. And we produce the text div. So we don't want to send the full cabal file, because that's expensive. Like if the cabal file is a couple of megabytes, sending it hence and forth is like unnecessary. And so we take the difference between the old cabal file and the new cabal file, and then only send what has been recently added. Good. Okay. So that looks easy enough. Are there any questions regarding what is the how we produce code actions? Now or never? Well, or later. Okay, then great. So then let's take a look. So we have skimmed over a couple details, obviously, because this is like a talk that has finite time, and we do not want to like explore the the internals of the cabal code base itself. I've skipped over how the third thing actually works, like how cabal-add implements stuff and how we find the actual component, but that's fine. We can just assume this is handled somewhere correctly. But what is not fine is the second step. What I said previously is that we do 2 things in this second step. First, we read the cabal file, we pass it to some intermediate representation, and then we pass it to our final representation so that we can work with it later on, and so that we can query it concretely. This is happening in the first thing, in the first 2 lines that we have here. In the second step, I said that we need to obtain the original sources of that cabal file. And if you have listened closely, I said reading the cabal file twice. So the issue is that I would have now is, does that mean in practice that we read the cabal file twice? That would be kind of inefficient, right? So since I'm asking like that, I think it's kind of obvious, or like probably people can guess what I'm going to say. Luckily, we do not pass the cabal file twice. So we do not recompute results unless it is needed. And this is also one of the cool features of HLS, because these expensive recomputations are avoided by using a so-called rule build graph. And we're going to take a look at what is a build graph and what are the rules that we are defining here. So first things first, rules essentially just define some computations for a file target. So you always run a specific rule for a file. So for example, you run the pass cabal file for some pass cabal file rule you run for some specific file, for some specific cabal file. Additionally, rules can depend on the results of other rules. So, and on the right side you can see these dependencies can be tracked in the build graph. On the right side you see what this build graph looks like for our particular handler. So we have 3 rules here. We have 3 rules that depend on each other. First, we have the pass cabal file rule, which passes our cabal file to its final representation, to its package description, which depends on an intermediate rule called the pass cabal fields rule. This rule, again, simply passes the cabal file to some intermediate representation. We're not going to talk about this in this talk. And this pass cabal file rules also depends on the rule get file content, since it needs to read the original cabal sources, right? And yeah, so that's the build graph that we are looking at. And what these rules enable us to do is they enable us to efficiently cache computation results. So once the result of a rule has been computed, we do not need to recompute it unless we know the result has changed. And yeah, unless the result has changed. Additionally, the build graph allows us to do another nifty thing, is we can, instead of demanding the latest result for a rule, we can also say, okay, what is the latest available result for a rule? So like we can have old results, we can obtain old results from the build graph. Why is this important? Well, for a quick IDE experience. Imagine you're modifying your favorite Haskell source file, and at the beginning everything's fine, it type checks, but then you enter some function and suddenly it doesn't type check anymore because that happens occasionally. Then the IDE can say, then the IDE cannot provide certain information. For example, it cannot provide any hover information for the parts that don't type check because it cannot work out the types, right? But what it can do is for anything that has been compiling correctly before that modification, it still knows from last time it type checked, okay, so for example, this identifier you haven't touched in forever, it still has the same type as before. And so these old results allow us to still provide like an IDE experience even when things do not work out, like even when things don't work right now, which is very helpful. How are rules defined? Rules, essentially to define a rule, the name of a rule is a simple regular data type. So what you see here, for example, at the very top, we have a very simple rule called pass cabal file. It has a single constructor called pass cabal file. And we define a certain computation associated to that rule using the define function that you see here. So this is an example, roughly what the pass cabal file rule could look like. To define, we pass 2 parameters. First, the recorder, which is a logging function. So in this case, it logs what rule has been executed and how long has it been executed, which is very nice for, well, performance metrics and obviously debugging. And then we take a function. Which specifies what action is executed when you want to have the result of the rule with the name pass cabal file. And what we return then, and then in between we do some interesting work. For example, we might do some kind of I/O. We might pass something, or we can do basically anything. And at the end, when all is done, we return 2 things. First, we return a tuple. In this tuple, the left element are the diagnostics. So diagnostics that we have found, things that we want to inform the user about when we were executing this rule. So for example, when we pass the cabal file, we realize this name is not actually known, and we report a warning to the user, or other thing, or similar. And in the right part of the tuple, we are returning an optional result. Optional because, well, sometimes a rule can fail. If we cannot pass the cabal file because there's like a severe error and we cannot continue, then we would produce no result. Then this would be a nothing. In this case, this is a just result to signal that we are returning some package description that we were able to pass. Yes, and again, to highlight, rules always operate on file targets. So we can run the pass cabal file rule on a specific file. Great, and how do rules now depend on other rules? Now we have an example to the left where we are reconstructing the build graph that we are seeing on the right. So you see here the top level rule is the pass, that doesn't work, is the pass cabal file rule. The pass cabal file rule, the first thing it does, it uses the pass cabal fields. When it calls use on another rule, then it signals to the build graph that it depends on the results of this rule, which is reflected in the build graph, where you can see now that the pass cabal file rule actually depends on the pass cabal fields rule. So when we would run this rule, the pass cabal file rule, we would jump into the rule definition of the pass cabal fields, which is down here. Yeah, I hope that's well, I hope that's readable. And what the pass cabal fields rule in turn does, it depends on the actual sources of that file that we're trying to pass, which brings us to the second part of this dependency graph, namely that pass cabal fields depends on the get file contents rule. While this build graph is linear, we can express any kind of build graph that is as long as it is acyclic. So there may not be any cycles. That would be bad. And how can we now use, and now going back to our code action handler, how do we actually use the results of this rule in our handler? So to do that, we want to query the build graph at certain points in time. We need some, and now finally we're coming back to this IDE state variable, which contains which is a collection of global variables, right? And the IDE state contains the rules of all plugins. So essentially, each plugin individually can contribute its own rules, its own extensions to this huge build graph, and that is globally known to the IDE state. And that allows plugins also to depend on the rule results of other plugins, which can be quite handy if they define a rule that is universally useful. So when we call run action E, this allows us to run a query against the build graph that is currently stored in the IDE state. We have a label here again, which is, as so often, mainly used for logging and for error messages. Always the two important bits. We need to tell people what's going wrong occasionally. So, and we run a specific query using this use function, where we say we want to use the result of the rule of pass cabal file. So we run the action associated with pass cabal file on this cabal file. Yes, and the underscore means that we are ignoring errors. So if there is an error, then we just say propagated error, throw an exception. We can't handle that. There are occasions where we could handle that, but here in this particular code action, there's nothing we can do about potential errors. And one other thing, what we have here is a normalized file path. What is a normalized file path in comparison to like a normal file path? Oh, that's not good naming. A normalized file path is essentially just a file path, but it is always absolute, so there cannot be relative file paths. And it has also been optimized for our specific needs in the language, in the Haskell Language Server. So in particular, it has a very efficient hashing operation and also efficient comparison. Okay, so that about rules. So how like what is the interaction of the build graph now with our code action handler that we've been trying to write. Here, now we see the subset of the code that we've previously been looking at. Nothing has changed. On the left side, we want to run two rules in quick succession after one another. And this is the state to the right, is the state of the build graph at the current point in time. In this case, the build graph has nothing computed yet, or no result has ever been computed, so we have never passed a cabal file, nothing of the sorts. And what happens then in the first step, is we are executing the first line. So we are saying, okay, I want to query the build graph and I need the result of passing the cabal file. So which is highlighted by this slightly bigger square bracket, like black borders. So that means that the cabal code action wants the result of that rule. And what does the build graph do? First, it will notice, okay, there is no result available right now, so I cannot provide any result right away. Then it will check its dependencies. In this case, the dependencies pass cabal fields, and check whether pass cabal fields already has a result. In this case, no. So we also need to recompute the result of the pass cabal the pass cabal fields rule. The pass cabal fields rule also does not have any result yet, so it will check its dependencies whether they are up to date. The same, so get file contents is the last dependency in that chain, and it has also never been computed. So we have never actually read the cabal file from the internals, like from disk, for example. And when we try to check the dependencies of get file contents, we see it doesn't have any dependencies, so we can just get started on computing the result of getting the file contents. So we just read the cabal file, right? And that updates our build graph. Suddenly, the result for the get file contents rule has been computed. And yes, so now that the dependencies of the pass cabal fields rule are up to date, we can also continue running the code associated with passing the cabal fields. And when that is done, the result is also the result is also updated and reflected in the build graph. So now these two rules, pass cabal fields and get file contents, are up to date. And now, since that all dependencies for pass cabal file are up to date, we can also just simply compute the result for that. We can pass the cabal file and so on and so on. So nice, perfect. So first, now we have the result in our hand and we can just work with it. Now the interesting parts come when we try to run this second computation, when we say, okay, I want to know the original sources, or like I want to know the sources of that cabal file. And when we take a look at the build graph, then we realize, okay, great, a result has already been computed. We check the dependencies of get file contents, whether any of the dependencies are marked as dirty, so that we might need to recompute stuff. In this case, get file contents doesn't have any dependencies, so the answer is yes, all dependencies are up to date. And so instead of rereading the cabal file from disk, for example, we can simply report the results immediately. And so we do not actually recompute. So we do not redo operations that have already been computed unless absolutely necessary. And that's basically why rules are so incredibly cool. They avoid unnecessary recomputations via this build graph. So it checks whenever something is outdated and only recomputes stuff when it actually needs to. Also, as already mentioned, plugins can define their own rules, so they can extend the global build graph that HLS has, and other plugins in turn then can also depend on these other rules to implement their own code action handlers, their own LSP handlers, which is quite nice. So that is basically how this code handler is implemented, and I hope now every line of this code example is clear. Are there any questions regarding this code example? Right away? No? Perfect. Okay. So since we have now computed the code action, we can actually start producing the results to VS Code. So we remember, this is now the other direction. Previously, VS Code sent us a request and asked us what are the code code actions available at this certain point in the file. The message router then asks each individual plugin whether they are capable of requesting to these kinds of requests. In this case, completions and GCIDE core cannot respond to code action requests, but the HLS cabal-plugin can, and it potentially produced a code action fix for that error in that file. However, additionally, multiple plugins could respond to that request. So for example, the HLS refactor plugin could see the error and say, okay, you are actually depending on another package that exposes a module that is very similarly named. So perhaps you do not want to add another dependency to your cabal file, you simply want to rename that import statement, which would be another code action fix. And since all plugins can, so in other words, all plugins can respond with potential code fixes. The message router then takes these messages and combines them in some way, or like takes these responses and combines them in some way. How they are combined, that depends on the LSP message. So for example, code actions, you can just take all code actions and show them to the user and tell them, look, I have so many ways of fixing this issue, and the user can then pick the best one. But some other requests actually do have some kind of priority system, or there shouldn't be actually more than one request. So take, for example, when the client asks us to, when VS Code asks us to format a source file, then there shouldn't be multiple plugins responding, okay, you can format it either this way or either this way. That would be detrimental to the overall UX. And this kind of completes the arc that we've been doing. So now what we've been exploring in this talk, we have explored the client-server architecture that powers the modern Haskell IDE experience. We have this code editor component, and we have the Haskell Language Server. And these two components communicate via the language server protocol. This language server protocol is quite handy because it allows HLS to support multiple code editors, like basically any kind of code editor, without additional maintenance efforts. So adding support for another code editor is no work, because HLS basically just adheres to the protocol, and the client just needs to make sure that it implements the protocol correctly. Further, HLS, as we've seen, features a very versatile plugin architecture, which makes it very much extensible and also, well, helps working on it because pieces of code are isolated into components, and so you can work on an individual plugin without having to understand the rest of the full architecture of HLS, because HLS in the end is a big project. Not as big as other projects, but still at least, I don't know, 250,000 lines of code. So understanding all of that is, for new contributors, impossible, but since the code is often isolated in small plugins, it can be quite easy to make contributions in these plugins. And at last, what we've also seen, HLS features a rule-based build graph, and that is very powerful. That's a powerful way to describe IDE workflows and to express dependencies between express computational dependencies. It also makes it. It also helps us to not think too much about the order of our computations, since we know the build graph will only recompute something if it's absolutely necessary. To the right, what you see as a reminder here is what the interaction between VS Code and HLS looks like when a code action is requested. So first, when you modify something, you change the Haskell source file, the VS Code sends a notification to HLS, which then in turn starts compiling or tries to process that change, and then based on this change produces new diagnostics notifications where it says okay, this is wrong, this might be wrong, or maybe in the unlikely case, everything's perfect, you did a great job. And once the user wants to fix some errors, they have to click on the specific error they want to fix, request code actions for that particular diagnostic, and then hopefully HLS is able to provide some potential fix. The user then has to decide whether they want to apply that fix, and once the user applied the fix, that information is then propagated to the Haskell Language Server. So to my hidden agenda actually, The HLS cover plugin is currently an experimental feature, so maybe you've noticed, but you have actually never seen the HLS cover plugin at work. So when you launch VS Code, excuse me, or Vim or Emacs, then you actually don't see any of the cool things I've just shown you. So it is an experimental feature that has been added actually a couple of releases ago, but it is hidden behind some. It is hidden. Let's put it like that. And we want to release it soon. But we need your help to actually make it ready for the actual real world. So we have here a couple of things that still need to be done on the HLS cover plugin. So foremost, for example, bug fixes. But also there are a number of features that you could implement, and if you're up for it, maybe even at this hackathon. That was my presentation. Thank you for your attention.
Yeah, thank you very much, Hannes. So, are there any questions for Hannes before we go for lunch? Yes.
I have a specific question. So, thanks for the talk. So, if the file changes outside of editor, let's say you use whatever editor or whatever other editor changes, does the HLS plugin, HLS in general detect it?
No.
Okay.
So when that happens, you change it from outside. The only hope that you have is that the code editor, for example, when you have it open in VS Code and Vim, and you change it in Vim and you don't have an HLS powered session, then hopefully VS Code will realize that you changed that file and then propagate that change to HLS. But HLS will not look at the physical file in general, since, for example, you can modify your source file, but you do not actually have to save it immediately, right? So there's a whole indirection happening called the virtual file system, which sits between the physical file system and Haskell Language Server. And so, in other words, we do not look at the physical file system, except in some exceptions, obviously.
There was another question.
Yes, I was wondering if, like, all these plugins, like with different priority, if they are all executed or only the one with the highest priority. Like, because we talked about like making it more efficient and so on, and if you execute like all the plugins and then throw away all the ones with the lower priority, it would be also maybe inefficient.
The priority is mainly for displaying information, and like the plugin priority is mainly for telling HLS which plugins it should give preference to. But we do not like decide what to respond to requests based on the priority. So is that the question, or did I misunderstand something?
Yeah, I thought maybe that the ones with the lower priority are not useful, but maybe they are still useful.
It's just like it's more like an internal thing, and well, actually there's two things. So for example, for internal things, when you have a notification and you see the Haskell file has changed, then the highest priority is to get this file to type checking immediately. So we want to give the user immediate feedback. We want the user to be able to see whether they have an error or something like that. And if other plugins in between were like, okay, now I'm taking resources here and I'm saying I want to provide some other IDE functionality which will be outdated anyway in a couple seconds later, then we want to give priority to the type checking plugin. Further, we can also use it to say in what order results are displayed. So for example, when you go to the hover information, when you hover over anything, what you see, what it looks like is you get one nice message, right? What this actually is 4 messages, where we say the one thing is the type, the declared type of that identifier. We have the documentation of that identifier. And then we also have the concrete type of that identifier. So, and how we display this correctly is can be controlled over the plugin priority as well. So it's a little bit an overloaded concept, to be honest. But I mean, that's just being overloaded in terms is just like, that's what you do in Haskell. So if anything is unambiguous, you're doing it wrong.
Any other questions?
So you showed the code snippet, and there was both a plugin M monad, but you also passed around this IDE state. Is there a reason why the IDE state is not part of the plugin monad, or?
I don't think so, to be honest. It's more like if you want to change that kind of code, you have to change a lot of code. And if it works, probably no one has actually like,
So what is the plugin M monad then?
So the plugin M monad is an imaginary monad that I invented for this talk. And what this actually is it is an error monad. So it's a transformer except T over the LSP monad. And so what this allows us is to exit earlier computation, but also get access to LSP-specific information. So because plugins sometimes need direct access to the internals, which is terrible, but that's the way it is right now. I hope it's not forever, but anyway. And this plugin M is, for the sake of this talk, is exactly that. It is basically an error transformer where you can exit from code pretty much like whenever you want. But you also have access to LSP-specific state and not to the IDE, but not the IDE state is not included in there. I think like maybe there's a technical reason, but at least from the top of my head, I think there is no technical reason why the IDE state isn't part of the plugin M.
And a second short question: here in the future of ALS cabal-plugin, do you also plan to include the cabal-check feature?
Yes, I want to. Like, actually, I think we should create an issue. Someone, please. But I think cabal-check would need to be optional because it displays information not immediately relevant to everyone. So I'm not sure how to implement it the least intrusive way.
What about potentially expensive actions, say cabal-check? Let's say it might take 10 seconds to compute. How does that fit into the whole model of performance in this model? If you have something like that you might not want to redo on every key press, is there sort of debouncing going on, or what mechanisms are there?
Yes. So yes. So exactly, there's debouncing going on. When there are there's debouncing going on in VS Code, there's debouncing going on in HLS. So lots of debouncing. For anyone not familiar with the term, debouncing means we delay a computation until we know that the latest result, when we know that there will not be any further keystrokes, for example, because if you enter something and then you make a short break and then you enter again something, you do not want to type check the file for each keystroke, not 10 files in 10 times in a second. That would be quite bad for the CPU, or the CPU would heat up. In HLS, we debounce those messages, and the whole protocol additionally is inherently asynchronous. So if cabal-check takes forever, takes a full minute to compute, then everything else will work then this computation will be computed in the background, and when it's done, and then you get the notification. It's a notification for that reason that we have additional diagnostics for the cabal-check results. So in theory, the IDE experience is not impacted in any way if any computation takes a prolonged time. Obviously, in practice, there's the obvious exception. Type checking must be as quick as possible, because otherwise the IDE experience will suffer.
Are there any other questions? All right, then let's give another round of applause to Hannes. Thank you very much.